this lecture, we will introduce indexing, slicing, and iterating of NumPy arrays. Indexing. Array indexing always use square brackets to index the elements of the array so that the elements can then be referred individually for various uses, such as extracting a value, selecting items, or even assigning a new value. So when you create a new array, an appropriate scale index is also automatically created. In order to access a single element of an array, you can refer to its index. So for example, A is an array with 6 values from 10 to 15. Then A4 will return the 5th value of this array. And the NumPy arrays also accept negative indexes. These indexes have the same incremental sequence from 0 to -1, -2, and so on. So A -1 will return the last element, and A -6 will return the 6th element from and counting from the end of the index of the array. And to select multiple items at once, you can pass array of index in square brackets. So if we want to access the 2nd, 4th, and 5th arrays, because these arrays are individual have individual index, so we have to put this index in an square bracket. Then it will be a double bracket after A. So moving on to the two-dimensional cases, they are defined by two axes, where axis 0 is represented by the rows and axis 1 is represented by the columns. Thus, indexing in this case is represented by a pair of values. The first value is the index of the row, and the second is the index of the column. So A is a two-dimensional array with 9 elements from 10 to 18. And the shape is 3 by 3, so 3 rows by 3 columns. Then A square bracket 1, 2 will represent the element at the 2nd row and the 3rd column. This element will be returned. The slicing allows you to extract portions of an array to generate new arrays. When you use the Python list to slice arrays, the resulting arrays are copies. But in NumPy, the arrays are views of the same underlying buffer. So this means if we use slicing to get a part of an original array, and we then change the value of this part of array, and the same positions value in the original array will be also changed. So slicing is a view of the original array. Depending on the portion of the array that you want to extract or view, you must use a slice syntax, such as you will use a sequence of numbers separated by columns within square brackets. So A here is an array with 6 elements from 10 to 15. So we use a column 1, column 5 will return an array which is a view of its original array, and in this viewing array is the 2nd to the 5th element of the original array. And you can use the 3rd number in the bracket to define the gap in the sequence of the elements. So here we add a column 2 here, so it will return the array with only 2 numbers, 11, 13. The gap is 2 here. And in a slicing bracket, if you omit the first number, NumPy implicitly interprets this number as 0, i.e. from the beginning initial element of the array. If you omit the 2nd number, this will be interpreted as the maximum index of the array. And if you omit the last number, this will be interpreted as 1 for the gap. So if we write 2 column here, So the gap is 2, and from the beginning to the end of the array with a gap of 2 will be returned. If we omit the first argument, then the view will from the beginning of this original array, and actually the result will be the same as this one. If we only write 5 here, then the gap will be 1 because this is a column here, and from the beginning of the array will be viewed. So from the first to the 5th element in this array will be the result. In the case of a 2-dimensional array, the slicing syntax still applies, but it is separately defined for the rows and the columns with a comma. For example, if you want to extract only the first row or the first column, you can write here A is a 2-dimensional array with the shape 3 by 3, and if you want to only return the first row of this matrix, then we can write this is first row 0 and comma, then with a column. Column means all the column of this row. And similarly, we can write column here with a comma, then 0. 0 means the first column. So all the rows item of this first column will be returned. If you want to extract a smaller matrix, you need to explicitly define all intervals with index that define them. So here, for example, we write A0 column 2, then comma 0 column 2. We return a small matrix then the result array will be 4 elements from the first to second row and the first to second column. This array will be returned. And if we want to index the rows or columns to be extracted if not contiguous, then we have to use a bracket here. For example, here we want to return the first and the third rows. Then of these rows, the first to the second columns values will be returned. Then we have to use a bracket here for individual rows. And iterating an array, you can use the for construct to do the iteration of the items in an array. So for I in A, if we can print all the values of this array. So if you apply the for loop to a matrix, it will always perform a scan according to the first axis, which is the row. First axis for the matrix is a row. So we can write a for row in A print row. Of course, we can use any variable name here. For example, we can for value, print value is the same. We also print each row of this matrix, but usually we write for row in A print row. Then each row of this matrix will be printed out. If you want to make an iteration element by element, you can use the following construct using the for loop in flat. So we can write, if we print all the I elements in an array with an array. Different here, because here is each row is an array. But here we can write item in A dot flat. In dot flat, then we'll make the matrix will be flat, element by element, one-dimensional, like so. Then we can print item. The result is an one-dimensional array. And if you want to launch an aggregate function that returns a value calculated for every single column or on every single row, there is an optimal way that leaves it to NumPy to manage the iteration. We can use the apply along axis function. This function takes 3 arguments. The first is aggregate function. The second is the axis on which to apply the iteration, and the third is the array. So if the origin axis equals to 0, then iteration evaluates the elements column by column, column by column. And whereas if axis equals 1, then iteration evaluates the elements row by row, row by row. So for example, you can calculate the average values first by column and then by row. So first we calculate the average value for this matrix column by column. So we can write np.apply underscore along underscore axis. Then we can write the first with the function first, np.mean. This is aggregate function because we want to calculate the mean of each column. And second, you can write axis is 0, means column by column. And the third argument is we can write ARR equals A is this matrix. The result will be this one-dimensional array, because column by column for this matrix, the average value for each column. And similarly, we can change the axis value to 1 here. Then we will get an array. Each element is the average value for each row in original matrix. And you can also define your own functions in using the apply along axis function. For example, we can write a function called define full axis argument, and then this function will return the half of x. So here we can write np.apply along axis, and the first argument is this function we have defined, and the second and the third is same as in the previous example. So this will return the half value of each row, and this will return half value of each column. Actually, these two statements will return the same result. Actually, it's also a matrix. And the conditions and Boolean arrays. An alternative way to selectively extract the elements in an array is to use the conditions and the Boolean operators. Suppose you wanted to select all the values that are less than 0.5 in a 4 times 4 matrix containing random numbers between 0 and 1. So A is a matrix. We use np.random 4 by 4. So the 4 by 4 matrix with random numbers between 0 and 1. Then we can write A less than 0.5. It will return a Boolean array with the same shape as this array, but the value is true or false depending on the value is less than 0.5 or not. Then we can write A square bracket A less than 0.5. It then will return a one-dimensional array with only the true value in these conditional arrays. We will show all these statements in Anaconda Spider. We check the file called section 10, the NumPy library, the NumPy library.py, and the link to this file will be put in the description of this video after the section has been created finished. So we move to the part called Lecture 4, Indexing, Slicing, and Iteration of NumPy Arrays. So indexing, first we import the library, then we create an array with 6 elements. We show A has 6 elements. The index A bracket 4 will return 14, the 5th element, and A bracket -1 will return the last element, and A bracket -6 will return the first element. And if we select 3 elements individually, we then use double bracket here. So the second, the fourth, and 5th elements of the original array will be returned. And for the matrix case, we create a 2-dimensional array. Show this array two-dimensional with 9 elements, 3 by 3 shape, and we return the second row and third column of this array is 15. Second row, third column is 15 here. And for the slicing, create an array with 6 elements. A is 6 element array. Then second to fifth element of this array will be sliced. Second to the fifth of this array. But just note, this is also a view of this original array. If we change the element of this part will also be changed. Then we use a gap tool. See how it is going. Then arrays 11, 13. From the second to the fifth, but the gap is 2, so only this one and this one returned. And we omit the first and second argument. Here we see. Then 10, 12, 14 will be returned. And we omit the first argument. The result will be the same as this one. If we only select the second argument, then it will be returned 5 elements. And for the two-dimensional arrays, A is a two-dimensional array with 9 elements. Then we can select the first row. We see the the first row is 10, 11, 12. And we select the first column. 10, 13, 16. 10, 13, 16. And we select a small matrix, small array. The first 2 row and first 2 column. Then this part will be returned. See, the first 2 row and the first 2 column. Then it will be this part. And iterating an array, can write for I in A print I. Then 6 elements will be printed out. For matrix, we can write for row in A print rows, and each row will be printed out. So 3 array, one-dimensional array. And we can write for item in A dot flat will print element by element. No bracket here. We can use aggregate function to calculate the mean value of by column of this matrix. The mean value for 3 column, and we can write axis 1 here to represent the row. So mean value for each row, 3 mean value here. And we can define a function called full, which represents the half value of each element. Then we can apply this function row by row for this matrix. The results row by row, each row's element is divided by 2, and we can apply in a column. You'll see column by column. Actually, this application for these 2 statements is the same, because divided row by row for each element is the same as divided column by column for each element. And this is conditional. We create a random number 4 by 4 matrix. A is two-dimensional array with 16 number and 4 by 4 matrix. Then we create a conditional array A less than 0.5. We'll see. So this will have the same shape as this original array, but the value is true or false depending on this conditional test for each value. with the original matrix. Then we can write a bracket a less than 5 inside. Then we will select only the true parts, only the choose value from these conditional tests. Then apply to this original matrix. Then this is a one-dimensional array with only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, only 10 values are true.